All right, everybody. Hello, Mr. Johnston here. We're going to take a look at how we can determine delta H of solution. These are calculations that you're going to see when you do your hot pack, cold pack lab. And these are also calculations that show up on the AP exam from time to time. So let's take a look. First, when we are doing coffee cup calorimetry, it is important to note that the heat lost is equal to heat gained. And another way to say that is Q is equal to negative Q. So when we think about this, we get an equation for how much heat Q is associated with the solution process. So we call that Q solution, which is going to be equal to negative MC delta T, again, because heat lost is equal to heat gained. And so for each one of these, the mass of solution, M solution, is equal to the mass of the solute plus the mass of the solvent. C for solution is about equal to C for liquid water, and this is for aqueous solutions. So that's the 4.18 joule per gram degree C. And of course, temperature change is temperature final minus temperature initial. So that's how we can determine the amount of heat, or Q, associated with the solution process. Now, delta H of solution, that enthalpy of solution, is always kilojoules per mole. So the units up here on the heat the heat associated with the solution process is calculated in joules. We need to change the Q solution to units of kilojoules. And we need the moles of solute, so we can convert grams of solute to moles. That means the units on delta H, or enthalpy of solution, is kilojoules per mole. Now let's take a look at this AP chemistry question. So this was actually from the 2010 exam. So a student performs an experiment to determine the molar enthalpy of solution for urea. We have the formula there. The student places 91.95 grams of water at 25 degrees Celsius into a coffee cup calorimeter and immerses a thermometer in the water. After 50 seconds, the student adds 5.13 grams of solid urea, also at 25 degrees Celsius, to the water and measures the temperature solution as the urea dissolves. And we have a plot of the temperature data is shown in the graph. So this question, we are asked to first calculate the heat of dissolution for the urea in joules. And that's where I'm going to use this equation. Q is equal to negative MC delta T. Now, remember that M, mass, is equal to the solution plus is equal to the solute plus the solvent. And so the solute is the 5.13 grams of urea, and the solvent is the water, 91.59 grams. So we have a total mass of solution is 97.08 grams. The specific heat capacity of the solution, we said that we can just use the specific heat capacity of water for these aqueous solutions. And then the change in temperature that comes from looking at the graph, I can see that the change in temperature is negative 3.2 degrees Celsius. So I simply plug those values in, and I get the Q for solution. Now, note that this is a positive number, which makes sense. The temperature dropped, indicating the process is endothermic, and an endothermic process, we know, requires energy, so it makes sense that that Q value is positive. So that's part one of this calculation. Now for part two, we need to find the molar enthalpy of solution. So that's Q of solution divided by moles of solute. And so the molar mass of the solution, if you calculate it, is 60 grams per mole. That's going to be needed when we go to convert from the grams of the solute to moles of the solute. So again, we take our answer from part 1, and we're simply, we got our answer for part 1, and we need to convert that to units of kilojoules. So I got, just divide by 1,000, I got 1.298 kilojoules. And now we're going to take the grams of the solute, the grams of solid urea, and convert that to moles using the molar mass. So I got the moles of solute is equal to 0.0855. And then it's just a matter of plugging them into this equation. So we take the kilojoules divided by the number of moles, and we got our molar enthalpy of solution. So my answer is 15.2 kilojoules per mole. And there we go, that's it.